Our next speaker, originally from Iran, who now currently lives in Montreal. He is a security engineer and smart contract auditor at Consensus Diligence. He's a current PhD student at Concordia University, and previously he was a blockchain engineer at BitAccess. Pleased to introduce Shayan Eskandari.
Thank you. Can you hear me well? All right. So yeah, this talk is more on the security and the differences of smart contract versus traditional software development. I just want to know how many of you have attended the Andrew's talk yesterday about fundamental of smart contracts? No one? I hope you're familiar with Solidity syntax because that's one of the requirements here. So I'm not going to spend that much time on this. This is just to give you an idea of what we're going to talk about. We're going to go through some of the vulnerabilities and then do actual hands-on code auditing. So thanks to Angela that introduced me. I don't have to talk about myself. So as we say, smart contracts are a new paradigm of software development. That means that it's interesting that if you coded before, it might be harder for you to do Solidity coding right now compared to people that have not coded at all. So what I'm talking about here, so let's say a simple application. I'm going to go through some of the examples. Let's say if you want to fetch an API, if you want to check weather.com for Denver's weather, you can use APIs into your software to call and get this information, or you want to get Apple's stock price. So let's say in a traditional programming, this is Python, a scripting language. I feel like there's an echo. In Python, the scripting language, it's just 2 lines. You import a library, you call that URL, and you get this information. That's all you need to use that information in your software. And now for Solidity, for smart contracts, do you think something like this would work? You just import that and call that URL? Any ideas that this would work or not, and why? Yeah. Why is that? Yeah, so that's a good point. It's external to chain. So there are some other reasons for that too. So first of all, who's calling this? So this is a screenshot of 2 days ago from Ethereum nodes. There are around 7,000 nodes running Ethereum blockchain. So not all of them are executing this at the same time. So if, let's say, you want to get Google's stock price, they might get the different times and different prices. And as you said, it's a closed system. Blockchains are running on internet, but they don't have access to internet. They just have access to all the information within that blockchain. So in this case, Ethereum just can't see any other Ethereum transactions. And this is also all deterministic execution. So if there is a difference in the information they get, and there's some randomness, it doesn't work that way. It should be deterministic. And also, all of these nodes should have a consensus on a final state to be valid. There are some projects, it's usually called oracles, that are supposed to be a solution for this external data, but this is not really in the scope of what we're going to talk about here. So one of the examples is here. You don't have access to the APIs, the same as traditional software development you have. Just one thing, timer is not going. I don't know what my time. So yeah, let's do another simple application. How do you password protect an application, like a password protected vault? So in traditional software development, usually you store the password in a database, check the input of the user to see if it matches that, and then open the application, right? So in Solidity syntax, that would be something like that. I hope the background is okay for you to see. So someone can call vault function with the password, it locks it, it saves the password in the variable called password, and then later on someone can come and call unlock with the right password. If the password matches the stored password, it unlocks the vault. So what is wrong here? Why this would not work in Solidity? Yeah, go. Yeah, exactly. Yeah, exactly. So other than the transaction sending to vault for password, The data stored on the data stored on the blockchain are all public, and there's no secret you can save on any of the variables. Even though variable is private, that's one of the common mistakes early on that people were making. So let's say if you want to use the traditional best software development best practice, which is store the hash of the password rather than the actual password. So in this case, Ethereum has this built-in, like Solidity has a built-in secure hash function called Kechek, which is almost SHA-3. It's a secure one, that's all you need to know. So in this case, you can store, you can lock the vault with the hash of your password and store that hash. And when you want to unlock it, you just pass the actual password. Solidity checks if that hashes to this hash and unlocks it. This seems like an okay implementation, right? But you would ask yourself, like, so the same, if someone calls unlock, everyone will see that password. And what is the point of this application? There is no point in like locking unlock. So let's make it more exciting. This password protect vault would pay 100 Ether if you can send it with a password. So the only line that is changed here is this line that is message just sender transfer 100 Ether. That means if anyone unlocks this vault, would receive 100 Ether. Do you see anything is this a good code, or is this also vulnerable to any kind of attack? Seems like a good one, right? So, but then the transfer is already done for the first transaction, right? There's no balance anymore. Okay, so this is why this code seems okay, but there is a fundamental difference in Ethereum and smart contracts that makes this code vulnerable, which we're going to talk about. And now I'm going to jump into enter the metrics. Oh, enter the Ethereum. That was a security of metrics workshop. Anyways, the best joke is the one that no one laughs. But so yeah, Ethereum is a decentralized public permissionless blockchain. So it's technically different than any cloud or online services. What do I mean by that? I mean that transactions or requests or any transaction that changes state has stages. They're not final right away. It's not like an API call or a server call that you change the state by just calling a function. So the stages are, user creates this transaction locally on their node. Then they broadcast it to the network, which is Ethereum network in here. And you should consider that like everyone else is doing the same. Everyone is generating these transactions locally, sending it to the network. And all these nodes have this memory called mempool, which just store these recent transactions. So these are not finalized transactions. They're recent transactions that are stored in the memory. And then miners would mine a block and might include that transaction. They get a bunch of those transactions from that network. They store it in a block, solves the proof of work puzzle, and adds it to the blockchain. So when the transaction is added to the blockchain, you could consider that the state changed. Then that function is actually called. So one point was that transaction have stages. The other one is the Ethereum incentive model, basically how miners behave. So you should know that blocks are scarce and block size is limited. So there is a market there for people to get in. This is because of the computation, storage, network, other reasons. And Ethereum, in order to solve this, introduced this concept of gas, which is similar to mining fee in Bitcoin, but a bit different. So if you want to define it, it's a unit of payment for the computation. So basically, you're paying for how much you want to compute. So this can be just sending a transaction, which is like really cheap, or calling a function that does some calculation. And it has a gas cost, like how much gas it requires for that transaction to be executed. So miners require a minimum number of gas in Ether to run that function. Now you can define a gas price, is how much you're willing to pay per unit. It's really similar to when you get gas for the car, that the price you pay is different per liter, it depends on where you go. And also a gas limit, which is the maximum amount you're willing to pay. You should consider that there is also a block gas limit, which every block can have a maximum gas limit. That means that you cannot do any complicated computation in one transaction. There's a limit to that on how much complicated you can have smart contracts. And the other thing is, so anyone can change the transaction priority by paying higher gas. So this is because miners behave on economic incentives. If you pay a lot of money to miners, they would mine your transaction first. So these concepts come in handy a lot if you have to have them in mind, especially with writing smart contracts. You have to consider how much gas you're using, optimizing it, and also the gas price that people can prioritize their transactions with. So now there is another concept that I want to talk to you about, which is an old concept called front running. It's been around since 70s in traditional stock markets. And it's basically, if you have a prior information of the market, you can do some action and profit from it. So the definition is a course of action where an entity benefits from early access to market information about upcoming transaction and trades. So in older times, it was mainly someone would hear someone wanting to buy an order, they would run in front of them to buy that order first. And that's because like the price would change after this other order comes in. So this is mainly because of your privileged position along the transmission of data. You could be the broker that buys that, and this is considered illegal in the stock markets. So now in blockchains, every full node is in this privileged position. All of them are seeing the recent transactions that are not finalized yet. So anyone can use this information to profit. Also, miners are a more privileged position. They can decide the order of transactions in the blocks they mine. So they can move transactions around. And also, as we said, miners can be bribed by transaction fee. Someone can pay them a lot more money to get their transaction mined first. In order to visualize that, so in top, you can see basically all the blocks in the blockchain. The red ones are uncle blocks. They're not really important for this talk. But you can see all those confirmed transactions. And all these down here are basically pending transactions, a recent transaction that are in the mempool. So miners would take some of the transactions of here, batch them in a block, and put them on in a blockchain, append them to the blockchain. So a bit more visualization, you can consider these as blocks in a blockchain. This is mempool. Front running is insert your transaction here, like anywhere you want, especially in the front of all the other transactions, but paying a lot of fees. So getting back to this example, if I call unlock with the right password to get 100 Ether, what can go wrong? So someone can front run me. Someone can see that transaction, send this transaction with higher fees, and get 100 Ether before my transaction gets through. So this is a fundamental difference with other software development. So everything seems fine here, even the hash is fine. But if I send that transaction, any other node can see that, send the same transaction with higher fee, and bribe the miners to mine the transaction before mine. So they would get 100 Ether, and my transaction would just fail. It would not fail, but there's no 100 Ether to send to me. So that was like one of the front-running attacks on Ethereum. It was a simple one. So yeah, as I said, anyone can front-run this transaction by higher fees and get 100 Ether. So one of the ways to solve this front-running, there is security by design sometimes means that like just remove this time-sensitive order in your applications. Sometimes it's not possible. So one of the solutions is this commitment scheme, or also commit and reveal, which means you have to break down your request into two transactions. One is the commitment transaction, which you would hash your information and send a transaction called commitment transaction, and wait for a few blocks, and then send a reveal transaction with the actual data. So the smart contract can get the data, hash it to see if it was committed before that time, and then run your code. So it can be used to prevent front running, for blind auctions, for gambling games, and a lot of other things. So now the exciting part starts. So code auditing. Have you guys done code review or code auditing before on any kind of code? Was that like on not smart contracts, right? All right. So you may know that like code auditing is not necessarily running tools. It requires a manual code review and in-depth understanding of the system, it's documentation to figure out if the code is actually doing what it says in documentation. There are security tools in the traditional software development. There are way more security tools, but in smart contract, there are a few that help you find common misuse patterns and where to look at. But still, you need to do manual reviews. And after a lot of hacks, for good or bad now, it's becoming industry standard to hire external code auditors. That means there's going to be a lot of jobs coming up in this field, but it requires a lot of expertise. So for the hands-on code auditing, I want to do a real-world application. This is basically the audit that we did around 6 months ago, and I want to walk you through one of the vulnerabilities we found. So Ethereum name service is one of my favorite services or dApps on Ethereum, which is similar to DNS, meaning that it's human-readable names to identify addresses for an Ethereum network. So let's say for DNS, your computer, you want to go to google.com, it basically talks to the DNS server, gets the IP address, and connects to Google server. Now for ENS, it handles .eth domains. So instead of giving someone your address as 0x6913, like all that hash, you can just say, send your ether to google.eth, and that's my address. Wallets can resolve that. And in order to buy these domains, it's on-chain transactions. You have to send a transaction to a smart contract, Ethereum ENS controller to purchase that domain. And it used to be blind auctions. You would commit to some value. 2 days after, you would reveal it and buy that domain. Now, on 4th of July, they switched to this instant domain purchase with rent-based, like similar to how domains work right now. But this on-chain, it's all on a smart contract. So there are a few points. One, that smart contract holds funds, like all these rents in that smart contract. No one else has control over that. And also because it's domain purchase on-chain, it requires this commit reveal scheme to prevent front running. Or else everyone can just buy the domain you want to buy and then sell it at a higher price to you. This has been around on domain names in early 2000s, and it's considered illegal right now. All right, so commit reveal is this that we talked about, that you commit to the hash of the data you want to buy, and then send another transaction to reveal that. So the smart contract can check that you were there first. Yeah. So I hope you install this Visual Studio Code and these extensions. The lighting is really bad here. But if not, I'm going to walk you through here. But it's really cool to have them installed for later on if you want to look at the codes. So if you have that installed, please go to this URL. It's the source code for ENS. But as I said, I'm going to do this on here too, but it would be cool to participate in this, all of them. So if you go to this URL, it goes to the ENS GitHub, the version for January 2019, and you can download the code, open the zip file, and open it with VS Code. Let me just. Is it better? Yeah. So just to know, is anyone doing this at the same time, or should I just go? Okay. All right. So I hope, I know Austin's talk was talking about the packages that you can use for smart contracts. So you don't really have to look at the other files. These are truffle package. So it's how you can deploy a smart contract with tests and other things. But all the contracts are in this folder, contracts. And for now, we go just on the main contract that is ETH register controller. So I just opened this up. I want to show you some of the tools that these VS Code extensions offer you that can really help you to understand the system when you open them. So up here, you see some additional functions here you can call. One is inheritance, which when you open a file, they can inherit other smart contracts, and it might not be visible when you look at the code. But when you click on this, it shows you how smart contracts are connected to each other. You can see ETH register controller is inheriting from ownable, which you can read on the code here, but it might not, as in a complicated smart contract, it might not be this visible. So this could be really useful. The other one is this graph. You can graph the whole system or graph just this smart contract, which in this case, you would see how functions are calling each other. This, again, could be really useful when you want to look at the big system to see how functions are looking at each other. So let's say for register, you can see what functions register calls, how they're related to each other, if it's external call, internal call. For in this case, it's not that much important. I just want to show you this because if you get time, you can use these to find some of the vulnerabilities. So one of the first things, it depends on the auditor. Everyone can look at the codes differently. Some like to do top-down view of the code. I personally really like to start with access control and transfers to see those are critical, and I want to see how they handle that. With that, I can see what the code quality is. So there are some modifiers that, like let's say only owner or is owner, that just checks if only owner of that contract can call, and also address the transfer of the transfers. So in here, is it big enough? Yeah. So in here, there are some functions like, let's say this function, it's called withdraw, which only owner can call, and it transfers all the balance of this smart contract to the caller, means the owner. So this seems fine, but as the auditor, this is a security consideration that anyone using this smart contract should know that owner can withdraw all the funds out of that out of this smart contract. And that's something that should be in the audit report. Okay, let's go on this. I just want to show you, like, these are the things you should look at, but they're not really exciting at this moment. The other thing is, so as I said, to prevent front running, it's using a commit reveal scheme, which the description based on the documentation is this. So you generate a commitment hash from the name you want to register, from the domain you want to register, and a secret. This secret could be a random number or the secret you generate. Then you submit this commitment value to the controller, to the smart contract. You wait for 1 minute or less than 24 hours. That's what the smart contract is checking. And then submit your registration request for the name and the secret. So if you have the code open in front of you, these are the functions basically that does all these lines. So make commitment is a function that is just view only, like it's pure, so you don't have to send a transaction. You can make the hash by calling this function. Then you send a transaction to commit to that value, and you wait. There's no function for that. And then you register with name, owner, duration, and secret. So in register, you reveal your secret and the name. Before that, the name does not touch the blockchain at all. So just to show you this in the code, so this is make commitment. That's all it does is gets a name and secret, and this is pure. So that means it doesn't change any state. It's not a transaction that people can see on the blockchain. It just returns the hash of these two. So just to make sure the front end doesn't screw it up, it's in this smart contract. So this commit would be the first transaction that the user calls with the commitment, and all it does is checks if it's not been committed before. If it's not, it just adds it to the commitment list it has. So I'm not going to go through all the code here. I'm just going to show you like some of the main important parts. One is here that, so you call the register with name, owner, duration, and secret. And it checks the commitment for name and secret, right? Then again, it checks if it's not expired. If it's expired, it would return the value to the user. It checks the rent, the price, if you send enough to cover the cost. It checks the label, and this is an interesting line because this line is where it registers that label or that name for the owner. And owner was an argument to this function, right? And then it returns the rest to the user. So to simplify this, this is what happens. You call make commitment with name and secret. You commit to that value, the output of that. And then you register your domain with name, owner, duration really doesn't matter here, secret, which you're revealing. What a register does, it checks the commitment with name and secret, and then registers the domain for that owner that you passed. Can you spot anything wrong with this process? It seems that is a good commitment reveal scheme. But that's kind of the thing. Owner does not exist in the commitment. So you're committing to the name, but you're not committing to the owner, who owns that domain. So if you commit anyone and then call the register and reveal your secret, anyone else can front run you and register and purchase that domain under their own name. So in order to understand this better, as I said, this register is vulnerable to front running. And that's because the commitment is not tied down to the specific owner. So for the audit reports, the best case is to say this is the bug, this is the vulnerability, and then come up with this attack scenario of like how this can be attacked. Mainly because while you're trying to do this, you either find more vulnerabilities or you realize that you're making a mistake and it's not really vulnerable. And also severity of that and priority of that comes in there. So here, Alice wants to buy a domain called my domain. So calls commit with the hash value of the make commitment with the my domain and her secret. Then Alice waits for 10 minutes and sends a transaction to register my domain for her, for Alice's address, and reveals the secret. Now Eve's looking at the mempool, and Eve sees that this transaction happening on the mempool. So now Eve submits a transaction with register, my domain, her own address, not Alice's address, and the secret that Alice revealed with a higher gas price. And she can win the race because it's paying high gas price, and miners would prefer to mine this transaction rather than Alice's. This would be an attack scenario. Do you know how to fix this? Like, what is the fix here? Like just exactly, the commit to the owner in the commit phase, and that was a simple fix. And as you could see, like if you have to look at the code more, but ENS team are really good developers, and this code was a good code. Like they considered having front-running prevention, like having commit and reveal they foresaw front-running and they tried to prevent that, but it was kind of missed there. And this is a bug that you cannot find with any tools. You have to read the specification, know the system, and know how that is working. Any questions so far about ENS? Is it interesting, just to know? So yeah, that's one of the things that you have to like read the code really and understand the system to be able to figure it out. How much we're doing on time? So there are like a lot of smart contract vulnerabilities in the last 2 years that we found out. This is that's really a nice categorization and chart that I found from that paper, the survey on Ethereum systems security. I don't know the authors, but I found the paper really interesting. So there are so many like traditional common vulnerabilities on smart contracts. There are underflows, overflows that we've seen on a lot of tokens. There are race conditions, which also it's called transaction ordering on smart contracts too. When you design a system and imagine that user calls the function A first and then function B, but anyone can call function B first. Like you're not really in control of that. There are uninitialized storage and functions, which, if you have heard of parity frozen ETH, was basically that. They had this multi-sig wallet, which used this library for their multi-sig. And there was like around, I forgot how much, but around $60 million worth of ETH restored in there. And the library was not initialized. So someone called in initialized and got to be the owner and then killed that contract. And all that money is just frozen on Ethereum for now, forever. But there are like some other smart contracts specific vulnerabilities that have not been around that much. One is reentrancy, which, if you have heard of DAO hack, was that you could call a function outside another smart contract or another address, and that that smart contract can bring back the workflow to to your smart contract and does some state changes. So the DAO hack, which resulted in $160 million hack, was just 2 lines of code. They had to be the other way around. It was like change the balance first and then send the transfer, rather than transfer and then change the balance. That was the fix, basically. Front running, as we saw, like front running is something that you don't look at when you're writing the code. Like, you have something in mind, but you don't see that what you're revealing, what you're exposing to the system. There are trusted actors, like as we saw in the withdraw transaction. There are actors in the system that are trusted. The keys could be compromised, and that could change the whole dynamic of the system. So these are the things that you should consider, especially if you want to do auditing. These are the things that should be on the auditing report. Upgradability is another thing. Smart contracts, as we know, they're immutable. You cannot change them. There are new patterns of upgradability, which you can have proxy contracts, and then that address is the same, but you can update the smart contracts that are underneath. That by itself is a security concern, because it can change the behavior of the system without users noticing that. Or frozen ether or tokens. Let's say you have this smart contract that is a game. You consider that it does not accept payments, but what if someone sends payments to it? Then you need a function there to be able to withdraw these tokens, withdraw this ether. If you don't have that, those ethers are lost forever. They're just stuck in that smart contract. We have a lot of these ether and tokens stuck in different smart contracts that cannot be withdrawn. And also, one of the main things is there are no randomness. As we said, this is a deterministic system, and there is no randomness within smart contracts. You can't really do gambling based on randomness. There are new ways. There are like ETH 2.0 is doing this beacon chain that helps with the randomness, but as of now, we don't have any randomness there. So yeah, Stefan Bayer will talk about more vulnerabilities in the next session. I'm not going to go into details of them anymore. And there are like resources that you can use to help you on either development or auditing. There are some good linters there. ETHLint is one of my favorites. It's really good. There are smart contract code analysis tools, Mythics or Slither. Mythics is by my team. Slither is another team. Also, as you have tested with Truffle, Truffle is a really good package for writing tests, but you have to write the test and also write the test for your tests, and it gets really test all the way down. There is this other Ethereum smart contract security best practices that it's open source and everyone can contribute to that. It's a really good start pack if you want to consider security on a smart contract and what patterns to use, what patterns not to use. And if you're considering auditing, smart contract auditing, I would really suggest reading audit reports that are out there. This is, I'm not sure if it's really visible, but this URL has like most of the concept diligence, like my team's reports there. We try to like make them all public. There are other teams that have reports out there. Read them. You can see the patterns that people have, the sections they use. There are a lot of commonalities in there, like what bugs are common there. This could be really interesting. If you're interested in like hacking or red teaming, as in security communities say, there are like these capture the flags challenges that are really interesting. They're on testnet. You can just get coins. Capture the ether is one. Ether not by Open Zeppelin is another one. So you can technically hack smart contracts, get funds out, get to be an owner of that. It's really fun. I would suggest doing that. And it gets really challenging too. And with that, I would just like to thank everyone at BTC 2019. And if there's any questions, I think we have 8 more minutes or maybe more. Yeah, so the question is for big smart contracts or big systems, what is the best way to split the smart contract and auditing, right? Did I hear it right? Okay. So so now we're seeing with especially 0x, Polymath, they are getting huge. They're like Aragon is one of the biggest ones. So every team are doing different method. Like Aragon is separating like access controls with like Vault with applications. But as we've seen, like with Open Zeppelin packages, there are it's really good to have these smaller modules and get them audited and then use them in different systems. But then the more you use, the more complicated your system becomes and the more unpredictable it becomes. That you might call, like let's say for Aragon, all the calls are basically proxy. And if you know how the system works, you know. If you don't, it's really complicated to start auditing a recent Aragon project. But it's going to be interesting to see how this grows. But the way right now people are getting more specialized in different projects, and they can only focus on that. That becomes like the guy to audit, like let's say Aragon. Like that's the only guy that knows how the system has evolved. Yeah. But using like audited modules like Open Zeppelin tokens, that's a good solution to like simplify your audit. All right. Thank you.